So now we are going to derive the statistics, the distributions formally. And for that, it's convenient to use the grand canonical ensemble. So remember that in the grand canonical ensemble, the number of particles is not fixed. It's controlled by the chemical potential. The chemical potential is the amount of energy you have to give to add a particle, right? Now, why are we doing the grand canonical ensemble rather than a canonical ensemble? It turns out that because there are constraints on what states are allowed and what number of particles are allowed as a consequence. Trying to derive in the canonical ensemble leads to you have to impose constraints on the particle numbers, which are very fiddly, which are very hard to implement. So it's easier to use the grand canonical ensemble. And then once you have derived it, you can always fix your particle number. So far what we have done is that we have considered say 2 particles. But now we want to find out what happens when we have an arbitrary number of particles. So the grand partition function. So by the way, the partition function for the grand canonical ensemble is called the grand partition function. So the grand partition function is given by symbolically. So for simplicity, what we're going to do is that at the beginning, we are going to say that we have only one. We're going to assume that we have only one energy level, E. But multiple particles can occupy that energy level. So if you have, say, 2 particles, then the energy will be 2E. 3 particles, then the energy would be 3E. Stuff like that, okay? So if I do this, then the grand partition function is very easy. You have sum over n, and E beta n mu minus E. Now, if I want to do this sum, if we have fermions, then by the Pauli exclusion principle, we can have only 2 scenarios. There are no particles with energy E in that state E, or there is 1 particle. There cannot be 2 particles because then the wave function would be, because of the antisymmetry, the wave function would be 0, right? So this is for fermions. But for bosons, there is no such restriction. N can be anything. So for fermions, we have the grand partition function is 1 plus E beta mu minus E, just 2 terms, right? But for bosons, we have an infinite number of terms. This is 1, and there's beta, sorry, not beta, e to the power beta mu minus e plus e to the power 2 beta mu minus e. So on and so forth. But this is a geometric series, and we have seen this before. This is nothing but 1 minus e beta mu minus e inverse, right? So in general, then what we have is that we have the partition function we can write as a log. Okay, before I do it as a log, let me just write it z. Z is going to be 1 divided by 1 plus for a fermion minus for a boson, then e to the power beta mu minus e, and then minus plus 1. And then if I write it as a log, then I have plus minus log of 1 plus minus e beta mu minus e. So plus for fermions and minus for bosons, okay? Now, we can also say, okay, what is the number of particles? What is the expectation value of the this is known as the n is known as the occupation number. And the expectation value is 1 over beta d of log of z by d of e. And that's just given by 1 divided by e beta mu, sorry, not mu, e minus mu plus minus 1, okay? Okay, so let's, any questions?
Is one of the plus minuses supposed to be flipped on that equation?
Sorry?
Wouldn't one of the plus minuses be flipped on the equation?
Can you repeat that? Sorry.
For log z.
Yeah. This one?
Shouldn't one of the plus minuses be flipped since they're flipped in the previous equation?
Do you mean the first plus minus? Do you mean the first plus minus?
Yeah.
Oh, he is saying the log z is equal to minus plus log. Yeah,
Yeah.
he is saying that. Shouldn't it be minus plus?
No, sir. It's because
No, there's a because it's below.
yeah.
Oh, I see.
Sir, like why? Like, could you just repeat why do we terminate the sequence for fermions after 1?
Because the occupation number of fermions can only be 0 or 1. If you have more than 1 particles, then the wave function, because of its antisymmetry, is 0.
Oh.
Remember that we cannot, for fermions, we cannot have states like this. Fermions. So yeah, we cannot have, that's what I meant. Otherwise, it would violate the Pauli exclusion principle. Okay.
Sir, we have mu in the equation of log z, right?
Yeah.
So mu means the particle number can change in the ensemble.
Yeah.
But we are considering only 2 particles in case of fermion.
Yeah, exactly.
So don't they contradict each other?
No, I mean particle number can change, but it can be either 0 or 1.
Oh, you mean the 1 or 0 are not particle numbers?
They are particle numbers, and that's exactly why we are not fixing the number of particles, right? It can be either 0 or 1. It cannot be arbitrary for fermions. That's the point. For bosons, it can be 0, 1, 2, 3, whatever.
Oh yeah, I got it now.
Okay.